Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, January 30, 2026. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a teeth-chattering, bitter cold evening here in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage, inform, and inspire people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has realized throughout space and time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, myriad Earth and space scientists, educators, and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, I'm excited to be hosting Sophia Ridolfo of the Center for Astrophysics, Harvard and Smithsonian. Sophia is a Fulbright scholar and Harvard PhD student working with Professor Lisa Kewley, director of the Center for Astrophysics. She is broadly interested in star formation and galaxy evolution. More specifically, she is interested in combining theory and observations to shed light on the physics of star-forming H2 regions and the interstellar medium. Sophia is originally from Australia, where she completed her undergraduate degree at the Australian National University in Canberra. In her talk this evening, Sophia will explore how galaxies build up their chemical elements over billions of years, from the smallest star-forming regions to the largest galaxies. She will discuss how stars forge new elements through stellar nucleosynthesis and how metals are redistributed throughout galaxies by mergers and by galaxy-wide inflows and outflows of gas. Finally, she will show how observations of the chemical makeup of galaxies provide a crucial fossil record of their formation and evolution. Along the way, she will highlight recent progress in this exciting field of astronomical inquiry. So welcome, Sophia. The Zoom platform is all yours.
Thank you so much, Bill. I'll share my screen now. Okay, can everyone see that?
Yes.
Yep. Awesome. Okay, I'll get started. So thank you so much for having me this evening. So I'm Sophia. I'm a graduate student at Harvard, and today I wanted to talk
Hold on.
evolution of galaxies.
Mhm.
And oh yeah, is
You're,
everything okay?
you're freezing a little bit.
Oh no, okay.
Try again.
Can you hear me?
Yes.
Okay. So today I want to talk about how we can use chemical elements to understand how galaxies form and evolve over the history of the universe. And so when we study galaxies, we're not just looking at a pretty picture, we're trying to, reconstruct a story based on a single snapshot. And so what I want you to keep in mind is that, galaxies are not these closed or static systems. They grow by accreting or acquiring gas. They form stars. They lose material through feedback and outflows. And all of these processes leave behind chemical signatures. And so we can measure these chemical signatures, things like, oxygen, carbon, and so on. And they act as a sort of archaeological record. And so when we read that record, we can reconstruct that chemical history of the galaxy. And so I'll start with a very broad introduction to extragalactic astronomy and then kind of zoom in on how gas and stars kind of cycle through galaxies. And then we'll focus on how we actually measure chemical abundances in the gas in galaxies. And then both in nearby and in the distant universe using telescopes like JWST. And so, as Tony pointed out, the background image is actually a FANGS image. It's a gorgeous image of NGC 1365, which is also a galaxy part of a survey that I'm working on at the moment that I'll talk about a little bit later on. Okay, so Extragalactic astronomy, starting very broadly, is the study of galaxies beyond our own Milky Way. And so one of the first things that we learn in, a galaxies class or astronomy class is that galaxies come in these very different shapes and sizes. And so you can see different examples here of a spiral galaxy, elliptical galaxies, and irregular galaxies. And so, spirals tend to have these, beautiful spiral arms. They can be very, we call them flocculents, or they can be called grand design spirals, have a lot of ongoing star formation that occurs throughout the spiral arms and have a lot of gas. And then you have these ellipticals, which are often dominated by older stars and can be redder and contain a lot less gas. And then you have irregular galaxies, which are usually smaller and less structured. And so the diversity tells us that galaxies, can evolve along all different paths, and this depends on, their mass, their environment, and history. But ultimately, they're governed by, similar, the same kind of basic physical processes. So you have gravity that pulls material together, you have gas cooling and forming stars, and then stars inject energy back into their surroundings. And so extragalactic astronomy allows us to compare galaxies, at all different stages of evolution and understand different mechanisms driving their growth. So galaxies outside of the Milky Way, we can take snapshots at all different, distances from us and try and use the universe as our laboratory, essentially. Okay. So now I want to talk a little bit about the baryon cycle. So this is basically describing how normal matter can flow into, through, and out of galaxies. So galaxies grow by accreting gas, often along these filaments of what we call the cosmic web. That gas then eventually cools and collapses to form stars. And so once these stars form, they don't just sit there. They, produce radiation throughout their lifetime, stellar winds, which can lead to stellar winds, which kind of rip off mass from the stars, and then supernova explosions once they die. And this injects energy back into the surrounding gas. And so this feedback can heat the gas, move it around, or eject it entirely from the galaxy in outflows. Okay, and then some of that gas is later recycled and then forms new stars, and some of the gas escapes into the circumgalactic medium. So that's the gas immediately around the galaxy. And so the baryon cycle essentially, it's how efficiently galaxies form stars and how they evolve over time. And so chemical elements, the key takeaway from this is that, chemical elements are created inside stars and then redistributed through this baryon cycle. And so when we study chemical abundances, we can trace each stage of this process and, understand the chemical history of galaxies. Okay, so as I mentioned, chemical abundances are a very powerful tool for trying to, understand galaxy evolution and the history of the chemical history of a galaxy. So this is because when stars form, they lock up the chemical composition of the gas at that moment. And then when they die, they enrich the surrounding gas with the newly formed elements. And so the metallicity, or the abundance of heavy elements in the gas, tells us how much star formation has occurred and how efficiently the galaxies have retained their metals. And so unlike, brightness or morphology, which can change very quickly, the chemical abundance of galaxies evolve over much longer timescales. And so this can make them very useful for reconstructing galaxy histories. And so for the rest of this talk, I'll show you how we define it, and then, why we use oxygen, and then observations as well of nearby galaxies and distant galaxies. Okay, so I'm sure everyone here is familiar with the periodic table of elements. Here, this periodic table comes from Chiaki Kobayashi's paper, where she studied the origin of all the elements and essentially how different elements are, the abundances grow over time. because of different sources and different mechanisms. So you have hydrogen and helium and lithium, which are the primordial elements and produced in Big Bang nucleosynthesis in the first few minutes of the universe. Every other element, so carbon, oxygen, nitrogen, iron, was created later inside stars. And so those elements are then ejected through different types of supernovae, which we call core collapse or type 1a, so supernovae and so on. And so when we observe metals in galaxies, we know that the stars must have already formed and evolved. Okay, so now this is the astronomer's periodic table of elements. So the early universe contained essentially no metals, only hydrogen and heliums. And then everything heavier than that, we call a metal. And so whilst in chemistry, this is, a little bit imprecise, in astronomy, it's very useful for studying galaxies because metals influence how gas cools, how stars form, and obviously how radiation interacts with matter. It also measures, it essentially measures how much processing by the stars has actually occurred, because the metals are elements produced by stars, not by the Big Bang. And so when we can say, a galaxy is metal rich or metal poor, we're basically making a statement about, its evolutionary history. So how much processing within the stars has happened, within multiple generations of stars and so on. Okay, and so now we can talk about oxygen a little bit more specifically here. It's one of the most commonly used traces of metallicity in galaxies, and it's the most abundant element after hydrogen and helium, and makes up roughly half of all the metals in the universe. So it's produced primarily by massive stars and then released into the interstellar medium, or the ISM, through supernova explosions. So that's partly the reason why oxygen is important, but it's also important because it produces these really strong emission lines that are very relatively easy to detect, even in distant galaxies. And so because of this, we use oxygen as like a proxy for metallicity in the gas phase. And so it tells us about, recent star formation and kind of the instantaneous star formation activity. Okay, so much of what I've been interested in trying to understand is in the chemical evolution of galaxies by trying to study the inner components and properties of the ISM in more detail. And so one way we trace this chemical history of galaxies and the buildup of elements is through the metallicity of the gas or H2 regions. So this H2 region isn't actually in this galaxy, but this is just to illustrate a point. So H2 regions or emission nebulae are ionized gas that surround recently formed young massive stars. And so these are really great sites for measuring chemical abundances because their spectra strong emission lines from elements like oxygen and nitrogen, which are good traces of the heavy element abundance. And so when we if we study H2 regions across an entire galaxy, we can map how metallicity varies spatially. And so these measurements allow us to connect, local star formation to the global evolution of a galaxy. Okay. And so just to kind of illustrate this point in a little bit more detail, the spectra of H2 regions provide a lot of different information. So you have these collisionally excited lines, for example, S2 and O2, which can act as probes of density. You can have O3, which acts as a probe of temperature, H alpha and H beta recombination lines, and then you can have ratios of different emission lines from the same species to give you the degree of ionization. And so these different diagnostics of, taking different emission line ratios allows us to build a very detailed physical picture of star forming regions. And these same techniques we use across entire galaxies. So, not just within a H2 region, but yeah, within an entire galaxy. Okay. So now going back to metallicity gradients. So many galaxies show these metallicity gradients. So if you draw a line from the center to the outskirts and then measure the metallicity in the center and how it changes going to the outskirts, then in a lot of spirals you will find a negative metallicity gradient. This is very typical. And the gradient reflects how the galaxy, it can reflect the inside out formation history of a galaxy and how it's grown over time, where it often forms stars from the inside out. But a lot of physical processes, for example, stellar feedback, gas flows, and mergers can steepen or flatten this metallicity gradient. And so by measuring gradients, we can get a lot of insight into how gas is moving within galaxies and how efficiently the metals are redistributed. And so metallicity gradients are quite powerful as kind of extragalactic archaeological probes. Okay. And so I talked a little bit about, how we measure gradients across a galaxy, but this has only been possible the past few decades because of IFUs called integral field units. And so this is a type of observing technique, integral field spectroscopy, we call it. And this allows us to take a spectrum at every position across an image of a galaxy. And so instead of getting a single metallicity measurement from like a single aperture, so you have one value for one galaxy, we can actually create two-dimensional maps which show how the chemical abundance varies spatially. And so IFU surveys have really revolutionized extragalactic astronomy by revealing all these complex structures that we previously couldn't resolve. And so these observations and this observing technique really provide a much more help us provide a much more complete view as well of how galaxies evolve. And so one survey I wanted to talk about, and some of the work I've been doing, is with what's called the Typhoon Survey. And so this survey is a survey of 44 nearby large angular-sized galaxies, which we observed using the DuPont telescope. It's a 2.5-meter telescope at Las Campanas, and has a mean spatial resolution, which varies from 10 to 150 parsecs, and which is quite well matched to typical H2 region sizes. And so the idea is that it uses what we call this prism method or progressive integral step method, where we take a slit and step across until we build the full field of view that covers the entire disk of the galaxy. And so that's why each galaxy image here is a different size, because essentially the field of view is customized for each galaxy, which is really cool. And so this technique results in this kind of pseudo IFU data cube. So we're using a slit here instead of that square IFU I showed you before, which is more efficient if you're covering a very large angular sized galaxy, and more cost effective than trying to mosaic an entire galaxy with an IFU. But the principle, the observing, in effect, it's the same. It's basically an IFU data cube. And so these are some of the highest resolution data cubes around. And so we can study these galaxies in really great detail and resolve individual star-forming regions, and then also measure metallicity gradients with very high precision. And so, so we have this, sample of galaxies that can also provide a benchmark for, interpreting observations of distant galaxies at high redshift as well. And so I wanted to show some results from this, so from 6 spirals in this Typhoon survey sample. So you can see these very pretty spirals, and then you can see that many of them, most of them have what you would typically see, a negative radial metallicity gradient, which is very much reflective of the inside-out star formation history. So this one here seems to have a very shallow gradient, interestingly. And then we can also look at other galaxies in the sample as well. So one of them I wanted to highlight was this beautiful one here called NGC 3109. And it's this nearby irregular dwarf galaxy. It's the closest one in the sample, so we have the highest resolution for it. And what I wanted to just highlight is how it looks, how different it looks at different wavelengths. So, you know, in H alpha, which traces the star formation activity, for example, you can see all these bubbles and really interesting, you know, clumpy morphological structures. And then, you know, in N2, for example, and O2, it seems to be a lot weaker and more concentrated towards the star-forming regions. S2 seems to be a lot more extended, and so on. And then you have a composite image here, where it just looks like this big blob. It's actually, yeah, a galaxy. Okay, so those were some results I just wanted to share. But now I want to talk a little bit about galaxies in the early universe. So I've shown you some very detailed observations of nearby galaxies from surveys like Typhoon. There's also FANGS, which Tony mentioned as well, which is incredible. I should have put some images in there actually, but you know, where we can resolve these individual star-forming regions and measure these chemical abundances with, yeah, very, very high precision.
Sophia, we
Yep.
have a question from Mario right now before
Oh,
you go into the early universe.
oh, sure. I haven't
I
been
can wait
keeping
to
track
the
of.
end. I raised my hand because I didn't want to interrupt you.
Oh,
Oh, sure. I haven't been keeping track of questions, but I can come back to those at the end if that's okay.
That's fine. Whatever's better for you.
okay.
Yeah. Let's do that. Okay, so when we observe galaxies at high redshift, we're seeing them at a much earlier time when the universe was, you know, younger and galaxies were still forming. But those galaxies were much harder to observe in detail. And so when we measure properties of those galaxies, we're generally only measuring global properties because they're so far away. We're not usually measuring, you know, the very fine spatial structure. So it's very challenging to try and interpret high redshift measurements using, you know, a lot of models and calibrations that are based on nearby galaxies. And so one thing that has, you know, revolutionized our studies of high redshift galaxies is the James Webb Space Telescope. So I kind of want to talk about this briefly because of, you know, how much impact it has. And, you know, there's a lot of interest in using chemical abundances to probe the growth and formation of galaxies at high redshift when, you know, the star formation rates were higher, gas flows were thought to be stronger than in the local universe. And measuring chemical abundances in these systems allows us to see, you know, what was the condition of these galaxies, you know, billions of years ago. Yeah, but as I said, it's very observationally challenging. The light from those galaxies is redshifted very far into the infrared, and so we need telescopes that are optimized for infrared. So for example, James Webb Space Telescope. So yeah, so it was launched 2021. It has this 6.5 meter diameter mirror, and it has, I think, 25 like gold beryllium plated hexagonal kind of mirrors that are all like joined together, which is pretty cool. And then, yeah, so as I mentioned, it's optimized for near infrared and infrared observations. And part of the reason why, you know, we need to put it in space is because it's so difficult to observe in infrared and near infrared in the ground because so much light, you know, and radiation in that wavelength range is blocked by our own Earth's atmosphere. And so we really need to go to space, but that makes it so much more expensive and challenging. And so now we finally have a very sensitive, powerful telescope that can look in this wavelength regime. Okay, and so now some really cool results straight from James Webb. So these are detected in the infrared so this is from the ultra deep field. This is basically a deep field as the Hubble Deep Field, I believe, but it can probe even deeper than Hubble. And so the galaxies that are detected in the infrared, this is because of as I mentioned, the expansion of the universe stretches their light to longer wavelengths, which we call redshifting. And so the galaxies that formed earlier in the universe emit most of their light in the UV and optical, mainly from the young massive stars. And so by the time the light reaches us, it's been redshifted into the near and mid infrared. And so JWST has really kind of revolutionized our ability to study chemical abundances, because now we can actually see these emission lines that you would typically see in optical that have been redshifted. So oxygen, oxygen is probably the main one here, but and then so these are integrated spectra for the entire galaxy, and then we can actually take a measure a metallicity for those distant galaxies. And so we can actually measure metallicities in galaxies only a few 100 million years after the Big Bang, which is very cool, and shows that galaxies can enrich themselves quite rapidly. And so this has really helped us put a lot of constraints on our own theoretical models and so on, and we can then compare it to our studies of local galaxies as well, and for example local galaxy analogs that might have properties that are similar to high redshift galaxies. Okay, so I want to just end it there for now, and I'll have a look at the questions. Brilliant and born. Okay, I think there's a discussion here. ISM stands for interstellar medium. Yep, that's right. Yep, so iron comes from massive stars and supernovae. James Webb is situated at okay, I think that's it actually. Did someone have a question?
Yeah, Mario wanted.
Yeah.
Is now a good time?
Yeah, of course.
So two quick questions. One is, I noticed when you did your spectra, you had H alpha and H beta, and they map the same. And as far as I know, the H beta doesn't really give you any more information. So I'm curious that you used H beta. Is there a reason for that? And does it give you information separate from H alpha?
Yes, it does. H beta is definitely important. So even though they're both recombination lines, and H alpha is the main one used to trace, star formation activity, because it's from the recombination from level 2 to 1 in 3 to 2 in hydrogen. H beta is important because if you take the ratio of H alpha to H beta, for example, you can use that. So we call that the Balmer decrement, and we
If we could, what? I'm sorry. What was that?
So if you take the ratio of H alpha to H beta,
Yeah.
and I believe Tony can also comment a lot on this as well. We call that the Balmer decrement, and we use that for dust extinction as just one example.
So for the bomber, okay. All right. And the second question I have is the formation of heavy elements seems to have occurred really early in the universe, and even from your own spectra, and it's steadily increased since then. What was the source, do you think, of much of the early abundances? Was it gamma ray burst type stars, which were abundant back then?
Sorry,
In other
could you
words, what
repeat
formed
that?
the heavy elements early on? Which stars did that? Was it the stars that created gamma ray bursters, which were huge stars?
Yes, so the most massive stars were more common in the earlier universe. So in the early universe, it would have been the most massive stars that were responsible for the heavy elements starting to be created.
Thank you.
I have a question.
Yeah.
So I saw something on YouTube, which was actually Facebook, which indicated that the iron in all of our planet's cores did not come from a small sun such as ours, but came from a very large sun. Is that right?
Well, no, it depends on the system. So it can be a low or high mass star.
Okay.
Yeah.
There was a planetoid, or maybe not a planetoid, but something in the meteorite belt past Jupiter, I believe, that was all banged up. It was a solid iron core, and the reference is made that it came from somewhere other than our own sun.
Oh,
Because yeah,
was this
Was it-
like a comet?
Was it Amu
Like,
Amu?
are you talking about Oumuamua?
I think so.
Yeah.
Yeah.
Yeah, Oumuamua.
So there were a few different theories for that. Some people went straight to aliens, and other people have come up with different theories. So I think one of them was that I went to this talk the other day by Jenny Bergner at Berkeley, who studies the chemistry of protoplanetary disks. And so one theory she came up with Oumuamua is that it might actually be this kind of water-rich like comet, and accelerated close to Earth. I think they think that the complex molecules that might have been, I guess, dissociated or something close to Earth might have provided that extra energy to kind of boost the object. And so that was one of the theories that, yeah.
And that
I've heard.
it contained elements in its wake. It contained elements that could not have
Yeah.
come from our own galaxy. Yeah.
Yeah, they're never going to figure that one out. Sophia, I got a question or two. First, when I was in Australia, I fell in love with the accent, so that's great. I wish I could get my AI to duplicate that. But the element chart you had that showed that were really the detritus of so many star events, different collisions, explosions. The elements that we're made of are really from just all the debris that happened for billions of years, I guess. And the other thing is the irregular galaxies. Are they being torn apart? Are they forming? Are they on the way to something? I mean, what makes them the way they are?
Yeah, so that's a really big question, and that's not something I can answer in a sentence, and it's an
Oh,
entire field of its own. So
disappointing.
like dwarf galaxy formation, for example, they're the most
Sure.
common galaxies. They're very faint and much harder to detect. Um, the one I showed you before, for example, NGC 3109 is an irregular galaxy, and it's very much dominated by its, ISM. And so we think that in dwarf galaxies, what we call pre-supernova feedback is what kind of dominates the galaxy's evolution. And so by that, I mean the feedback or stellar winds and radiation from massive stars. So before the stars have died, so before supernovae, so pre-supernova. So we think that's one mechanism for one of the biggest or main mechanisms for dwarf galaxy growth and evolution. But there's a lot of other problems. There's a lot of other tensions as well, especially on smaller scales that also relate to like Lambda CDM
How
cosmology
big
as well.
how big are the irregular galaxies? How do they span? What's their distance from one end to the other of these things?
Yeah, so the ones I was looking at, so the one I showed you was 10 to the 9 in solar masses and spanned maybe something like kiloparsecs in scale. I can't remember off the top of my head, but Yeah.
Okay, thank you.
Yeah,
Great
sure.
job.
Oh, thank you.
Okay, I think I'll get into the weeds here, Sophia. Uh, having to do with the measurement of oxygen.
Yeah,
Um,
sure.
because your ratio of the oxygen abundance to the hydrogen abundance is your measure of metal abundance you use. And so my question is whether you use the emission lines from both doubly ionized oxygen and singly ionized oxygen to capture it all. Do you have that sensitivity to catch the
That's a great question. So there are actually different methods that I didn't go into because it's very technical, but there's different
Mhm.
methods of measuring metallicity in the gas of oxygen. So the two main methods are firstly what we call the strong line method. And so these are basically strong emission line ratios that are detected in H2 regions that have been shown to correlate with metallicity. And then the other method is what we call the direct method. And so we call it the direct method, but it's not that direct or straightforward. But this method is essentially you are using what we call collisionally excited auroral lines. So these are higher energy level lines of, for example, oxygen, like the O34363 line is the most common line that we use for the direct method. And then also O2, the 7300 lines. And so you use those we use what we call these temperature sensitive line ratios, which is a ratio of the higher energy auroral line to the lower level nebula strong line. And then that gives you a temperature sensitive line ratio. And so that gives you a measure of the electron temperature, or essentially the temperature of the electrons that are colliding with the ions to produce these collisionally excited lines. And then we also need a measure of electron density. And so you can use different emission lines, also collisionally excited lines, but generally you want two lines that are closely spaced that minimize the dependence on temperature or energy and are sensitive to the density because they have different critical densities. And so this gives us a probe of electron density. And so how you actually get the abundance from those two is that the direct method or ionic abundances are explicitly dependent on the temperature and density. And so for the case of oxygen, we get an ionic abundance from O2 firstly, so singly ionized oxygen, and then O3, doubly ionized oxygen, and then you add them together to get the total oxygen abundance. And then this is assuming that, it's not super excited and we don't have like O4, for example.
Sure. Thank you.
Sophia,
Yeah.
are you also studying biochemical formation? I'm fascinated by that.
No, I don't do any biochemical
Okay,
stuff.
I'm fascinated that.
My main expertise is in spectroscopy with IFU spectroscopy of H2 regions and galaxies. So
Okay, thanks.
yeah, but there's definitely crossover. I'm sure with so my office mate, for example, she studies protoplanetary disks and she uses spectroscopy as well. And she uses very similar techniques, so using line ratios and line diagnostics, except with molecular lines, because in protoplanetary disks, they're very cold. They're at temperatures of around 100 to 1,000 Kelvin. And so you have to use different, and they're also mainly molecular. So they're very cool. And so you're not probing the same kind of we're not probing, for example, warm ionized gas in a H2 region. We're probing, very cold molecular gas. So we need to use, we need to use instruments that are sensitive to different wavelengths and atomic transitions. And so we'd use ALMA, for example, to look at a planetary disk and, use line diagnostics for that.
Thanks.
Okay, I have another question.
Yeah,
Um,
sure.
one of the main results for the nearby galaxies is that you have is that they evolve from the inside out, and you could tell that by the gradient, the radial gradient in the oxygen abundances. So
Yes.
that's pretty cool.
Yeah.
Um, they also see similar radial gradients in the colors of the stars in these galaxies. Um, and so I'm just wondering whether you have had a chance or your team has had a chance to compare those respective radial gradients, the radial gradients in the color. In other words, it goes from yellowish from the inside and then out to bluish in the outside of the galaxy, uh, which is consistent with the inside-out evolution. I'm just wondering whether that has borne fruit, that comparison.
Yes. So this survey isn't high resolution. Well, what I what is more accurate to say would be these galaxies are too far away to resolve individual stars. So
Right.
there are more nearby studies where you can directly compare the stars and the gas and do a comparison of gas phase and stellar metallicities, and people do that. So I've only been looking at the gas phase metallicity. As far as I'm aware, I think they are very similar and trace sort of a similar kind of formation history. But that was really interesting what you were saying about the radial gradients of the colors. I haven't.
Right.
Uh,
Those are like integrated colors. That it's not,
yeah,
but it's not at that high resolution.
yeah, yeah. So we can't do, for example, a stellar metallicity gradient with this sample. Um, but yeah, I'm sure there's. I can't think of any surveys off the top of my head where you can do it with, but yeah, there's definitely some out there, I'm sure.
Okay, good. Yeah, it's definitely worth checking out because there's a lot of they
Yeah.
tend to compare oh, U band, visible band, and things like that for the color, and you can just see it in color pictures of galaxies, like what Mario would make. That the inner parts of a spiral galaxy is yellower than the outer parts, which are bluer.
Yeah. Yeah, that's really fascinating.
Oh, we have Bill Wall wants to ask a question.
Oh yeah, please.
Yeah, I don't know if this your talk is over yet or not. Is this just a sort of an intermission where we ask a few questions, or are you going to talk a bit more? I was going to ask my questions at the end if
Oh, no, please go ahead. I'm happy to talk more about my specific research if people would like. Otherwise, I'll just leave it there. And I'll keep taking questions.
yeah. Okay. Well, I have questions about systematics, how things may vary. Like if you were mentioning you have certain lines that you can use for pairs of lines that you can use for getting densities and others that you can use for getting temperatures as well, and that helps
Yeah.
you nail down the abundances. So
Hmm.
I was wondering, do you see systematic differences between, say, low redshift galaxies and high redshift galaxies? And then I have the same question. I don't know if you have enough information or enough data between the arms of spiral arms. I have the same question about arm to interarm differences, abundances and temperatures and densities. What can you say about that?
That's a super interesting question. Okay, so I'll answer the second one first
Hmm.
because one of the galaxies in this typhoon sample, we have actually looked at how the gas phase metallicity varies along the spiral arms and looked at the difference between the spiral arms. And they did, people did find that they actually varied, and that was really interesting to see. So, and they looked at how it varies azimuthally as well. So that was super cool to see. Your first question about how um,
That was
abundances
about
vary
yeah
between
between the early
low.
universe and the recent universe. How does it vary with very young galaxies to recent galaxies? How do those things vary?
Yeah, yeah. So I mean, I haven't done a direct comparison. I guess because I'm not working with high redshift data, but I would expect high redshift galaxies to maybe be more metal poor, but it really depends. I'm not entirely sure because I haven't studied high redshift galaxies specifically.
So I was wondering if there would be something like if they're metal poor, then you see the H2 regions are warmer. I was just wondering if there's any kind of data to support that.
Yeah. That was okay. That was me really just speculating on the spot, but let me think. What have we actually seen? So we've seen these nebula-dominated galaxies, which have very strong nebula emission lines. We've also seen nitrogen-enhanced galaxies as well, which has been very fascinating to try and understand where that comes from. Like the enhanced nitrogen relative to what we'd normally see. So there is that. I'm not sure about oxygen, though, specifically. Yeah.
Can we hear about your specific research?
Yeah, sure. Yeah, I was debating whether or not to go into it because it's like really niche, but I can yeah, talk about that for the last sort of 15 minutes if people would like.
Yes.
Okay, sure. Okay, so I had a little question slide and then okay. So I'll basically just start with this little animation. Actually, let me start that again. Okay, so in nearby galaxies, we can resolve these, individual H2 regions and, even study their internal structure. Historically, we put single apertures on them, which kind of masks or averages out all of the emission. But now with IFUs, which I talked about, we can actually look at how the spectrum changes across the entire H2 region, so across the field of view, which is really awesome. And that's really important because that allows us to actually look at these variations in temperature and density, which in models we assume is uniform, but we know that it's not a realistic assumption. So we know temperature and density are supposed to vary throughout H2 regions. They're very complex. And now with IFUs, we can actually spatially resolve them and map these internal variations. And so this is important because the variations can bias our, measurements of the metallicity. And so to study this in a bit more detail and try and understand this bias, we use deep IFU spectroscopy of H2 regions in the Magellanic Clouds. So using the WISE IFU on the ANU 2.3 meter telescope. And so we use these three H2 regions in the Magellanic Clouds. So they're very nearby. They are compact, so they fit within the field of view, and it means that we can just spend like the whole night pretty much pointed on this one H2 region. And that's really great because that means we can get detections of these really faint auroral lines that we need for a direct metallicity. And that means we can study the different physical properties that might bias a metallicity measurement. Okay, so here is an example of some signal to noise maps for one of my H2 regions. So there's only 3 in the sample because it's difficult to get this kind of data, but you can see that we have decently good signal for the 034363 line and the O2 auroral lines. And one IFU kind of literature we call SPAXEL, spatial pixel, corresponds to 0.2 parsecs. So this is actually sub-parsec scale observations, which is really, really cool. Okay, so I'll briefly kind of explain the electron temperature, kind of how we measure that again. And so this is part of characterizing, the physical conditions in a H2 region. And so we use the ratios of auroral lines at higher energy levels to lower energy levels. And so they come from, energy levels with different excitation energies. And so a stronger auroral line, like a stronger higher energy level auroral line indicates a higher temperature. And so one of the most widely used temperature diagnostics is, there we go. So you get a temperature sensitive line ratio. And so one of the most common ones is 034363. It's very faint because metals act as coolants. And so when you have a higher metallicity, you end up with much weaker auroral lines. And this is exacerbated when you go to spatially resolved scales across a nebula because you're spreading out the photons, right? And so you need to integrate or basically observe for even longer to try and get that detection. And so that's why we need deep IFU observations of these regions. Okay, so now we can characterize these H2 regions or these temperature variations for two different zones. One of them is called a high ionization zone. And this is characterized by the O3 temperature sensitive ratio. And then the bottom row is the O2 temperature sensitive ratio. And so these trace the temperature structure across two different ionization zones in the nebula. And so you can basically see that the temperature varies in all of the H2 regions, but it might look different depending on the ionization zone. And the more ions you have, or the more temperature sensitive line ratios you have access to, the more complete the picture you can build of the ionization structure of the H2 region. And so we can then look at how the ionization zones correlate with each other, so how they, vary. And we see this really big scatter in the O2 temperature and a very kind of much more uniform distribution in O3. Okay, and so electron density I mentioned comes from these closely spaced energy levels from the same ion, which have different critical densities, and so they become sensitive to the gas density. So at really low densities, you have spontaneous decay dominating, where the lines intensities peak, and then at the highest densities, you get collisional de-excitation dominating, which suppresses the line densities. And so the densities of H2 regions in the ISM, the O2 and S2 ratios are very good probes of density. Okay, so we can look at electron density variations now in the O2 and S2 density using the O2 and S2 density doublets. And what we can see here is that this one's my favorite actually. So the middle bottom panel, you can see these really interesting filament structures. And on the right, you can see these really interesting clumps of density. So there we go. Yeah, really interesting clumpy and filament structures. And same as before, we can look at electron density variations, 1-to-1 for some of them, but a bit of scatter in one of them, interestingly. Yeah, we weren't sure what that was from. It might just be because they trace slightly different densities or something else that I'm not sure of. Okay, so you have ionization parameter as well, which is essentially the strength of the ionizing radiation field from the young stars. Because we're looking at compact H2 regions here, essentially there might only be like one star in the center. And so, what we expect for an ionization parameter is that you have the highest ionization parameter in the center where the most ionizing photons are, and then it basically drops off as you go towards the outskirts, which is what we see here. Whoops. Okay. And so we can basically estimate this, or people typically estimate this by taking ratios between emission lines from the same ion, but with different ionization states. So like O3 over O2, for example. Okay, so one thing I also looked at was variations in both the direct and strong line calibrations. So I talked before about the direct method. Here are some maps of metallicity. So we add the low and high ionization zone abundances, and that gives you the direct metallicity. And then here are some of the strong line calibrations I used, using different combinations of emission line ratios. So these are some commonly used ones, and I tried to aim for a variation in, different combinations of emission lines used. But what's interesting about this is if you actually take the difference between the two, so basically subtract off the strong line calibrations from the direct method, what we found is this interesting difference, or like residual map or discrepancy map, where we find the biggest differences are occurring on the edges. And this is important because we can actually spatially resolve these differences, whereas previously people had only been able to compare this on an integrated basis. And so we look at these temperature fluctuations as one potential contributor. We already know that it contributes to the and biases the direct method. And so we wanted to look at whether it's biasing this discrepancy and also the other method. And so the advantage of this IFU data is that we can actually look at spatially, we can look at different physical properties and look at what can we link to this discrepancy. Okay, and we do find that temperature fluctuations actually do correlate with the direct metallicities. So this is the low ionization zone abundance. It doesn't really correlate with the high ionization zone abundance, interestingly, and the direct metallicity. So this is adding both of these two together. And so then you should get a correlation here. We're defining the temperature fluctuations as being the difference between the O3 and O2 temperatures. And then each data point here corresponds to one little pixel here. And then each color is a different H2 region. And then the stars are the integrated values. Okay, but the integrated metallices are a representative average. So you actually don't really see these variations if you're just putting, if you're just observing the integrated H2 region, which is really interesting. And then similar to before, we find that these temperature fluctuations do correlate with the difference in metallicities. And then finally, we find that some strong line ratios are actually more affected by the temperature fluctuations than others. So for a strong line ratio to be a good indicator of metallicity, we want it to be insensitive to temperature fluctuations, right? But we find that this scatter here for most of them means that at least in our 3 H2 regions, so it is a very small sample, but at least in the 3 H2 regions we checked, the emission line ratios are or do have some sensitivity to temperature. We do see that for N2S2, the N2S2 based ratios, there might be some insensitivity there. And so we think that they might be better indicators than the others. And then lastly, we also looked at what we call line of sight radial gradients. So we basically looked at how does the gradient vary across different lines of sight. And then, for ionization parameter, what we kind of expected is that it would look isotropic, so the same in every direction. But for density, it looks very different. And so this just tells us that, a single radial gradient is not really sufficient to capture the complexity that you see in H2 regions. Okay, and so the takeaway is that integrated H2 region metallicities are very representative of internal structure. Both direct and strong line metallicities are impacted by temperature fluctuations, and then a larger sample of spatially resolved H2 regions in a range of environments is what we're getting at the moment. So we have a lot of observing time. So I've got some observing time with Magellan, and then we recently got 100 nights with the ANU WIFE's IFU to build a much larger statistically significant sample. And so this will help us add constraints. And then we'll also be able to compare this with photoionization models as well. So for example, mappings and also mappings 3D, which take into account the 3D geometry of H2 regions. Okay.
Wow. So you guys asked for it.
That's great. Thank you very much.
Yeah, so that is my that's my research.
Yeah, it's cutting edge. It's really good stuff.
Thanks.
We had one question about whether the telescope I guess your ANU telescope uses adaptive optics.
Yes, it does, because that is a very important point. Because if you don't use telescopes with adaptive optics, especially on large, like galaxy scales, like this has been shown to actually affect metallicity gradients and can actually flatten gradients. And I would expect the same effect on the small scales with H2 regions as well. The only drawback here is that I would say ANU at Siding Spring, unfortunately, doesn't have great seeing.
Well, the adaptive optics should help.
It should help with that, yeah, but you know, it's not probably going to compare to my Magellan observations, but that's okay.
100 nights is pretty awesome.
It is pretty good, yeah.
Yeah.
So I'm a co-I on that program, and so we started last semester, and that will go for the next 2 years. And then last semester, I also started getting my own PI-led Magellan observations, and so I'll keep going with that, and yeah, see what we can find out. And yeah, I started. So with Magellan, we started getting observations with this newly commissioned IFU called Yarmouth. And so that will be very exciting. That was commissioned a year ago, so it's brand new instrument, very exciting.
Bill Wall, would you like to have the last question?
Sure. Yeah, it's a question I put in the chat. That's I mean, you have basically density maps and temperature maps, and so you can actually look for correlations or anti-correlations between densities and temperatures. And I
Yes.
can think of arguments for
Yes,
either one of those.
we
But
did check
what do you see?
density. We did check density as well, and it actually didn't have an impact for our 3 H2 regions. But that doesn't mean, obviously, you know, on a more general, you know, it doesn't mean that density wouldn't have an impact.
Yeah,
It
but I
was
mean, do you
just- it
see
was
that
just
like
what we
are they
saw.
correlated or I mean, it's like
No,
the
we saw
density
no
temperature.
correlation with density, which was
Okay.
really interesting, and I was kind of surprised by that.
That there wasn't that there was one or there wasn't.
There wasn't.
Okay.
I thought it might be because there might not be strong enough density clumps to actually maybe have an impact, but I'm not sure. But that's why
It's just
that's why we need a much larger sample to actually
yeah.
kind of disentangle this.
Yeah, because if they're anti-correlated, you'd expect that for pressure. If it's all pressure, it's all the same pressure and so on. It'd be pressure equilibrium. But I don't think you'd see that in an H2 region. They're very dynamical, so I'm
Yeah.
not surprised that you don't see the correlations. Thanks.
Well,
Yeah, thank you.
lots of questions that remain to be explored. Sophia, this was great, and I'm glad you had a chance to show your research. And I want to thank you, and we'll make sure that it goes up on the YouTube channel, but until you give the go-ahead, it'll just be sent out to my listservs.
Yeah, sure, no worries. Thank you so much for having me. And yeah, it was really great to chat with everyone and discuss science.
All right.
Thank you
Thank
very
you.
much.
Thanks a lot. Thank you.
Great talk. Thanks so much, Sophia.
Thanks,
Thank
Bill.
you. Bye-bye.
Bye.
Thank you as always, Bill.
As always, Patty.
Patty.